It turns out Laplace transforms can be used to solve systems of linear differential equations, and that's what we're going to do now. Our system is dx dt equals 2y plus e to the t, dy dt equals 8x minus t, and we have initial conditions x of 0 is equal to 1 and y of 0 is equal to 1. The basic strategy is to apply the Laplace transform to both equations and then work with them after we've done that. And remember that the Laplace transform converts a differential equation into an algebraic equation, and so the rest of it looks kind of like substitution, and then, we'll see. It's important here to keep an eye on your notation. We have functions x and y, and then we have our independent variable t. When we transform the function y of t, we're going to write uppercase s. And when we transform x of t, we're going to write uppercase x. And so, the notation can be useful provided it's used correctly here. Applying the Laplace transform to the first equation gives us s x of s minus x of 0 equals 2 times y of s plus 1 over s minus 1. Of course, x of 0 is equal to 1, which we'll write when we rewrite this. Applying the Laplace transform to both sides of equation 2 results in s y of s minus y of 0 equals 8x of s minus 1 over s squared. Substituting 1 in place of our x of 0 and y of 0 terms, we see that we have two equations that have uppercase x and uppercase y in them. Those are our unknowns. There are different paths we can take here, but what I'm going to do is solve the Laplace transform of equation 1 for y of s, uppercase y of s, and then substitute it into the Laplace transform for equation 2. For equation 1, we get y of s is equal to 1/2 times the quantity of s x of s minus 1 minus 1 over s minus 1. Combining the negative 1 and the minus 1 over s minus 1 gives us 1/2 times the quantity of s x of s minus s over s minus 1. Putting that into the Laplace transform for equation 2 gives us s over 2 times s x of s minus s over s minus 1 minus 1 equals 8x of s minus 1 over s squared, where we've just substituted in place of y of s. Clearing the denominator of 2 and then gathering all of our uppercase x's on one side results in s squared minus 16 times x of s is equal to s squared over s minus 1 plus 2 minus 2 over s squared. Getting common denominators and then isolating x of s gives us x of s is equal to, the numerator is s to the 4th plus 2s cubed minus 2s squared minus 2s plus 2 divided by the denominator s squared times s minus 1 times s plus 4 times s minus 4. And I encourage you to work out those steps to make sure you get the same thing that I have here. After performing partial fraction decomposition, we get that x of t is equal to 1/8 t minus 1/15 e to the t plus 173 over 192 e to the 4t plus 53 over 320 e to the negative 4t. And yeah, I actually worked all that out. See, here it is. Okay, well, enough of that. Now that we have x of t, I know we need y of t. Equation 1 gives us a nice means to find y of t. We can solve dx dt equals 2y plus e to the t for y. Doing so will give us that y of t is equal to 1/2 x prime of t minus 1/2 e to the t. Differentiating x and then substituting here and simplifying gives us that y of t is equal to 1/16 minus 8/15 e to the t plus 173 over 96 e to the 4t minus 53 over 160 e to the negative 4t. I've put them together here for good form. It's good to do that when you have a deliverable. Let's see if this next one is any easier. We've got d2x dt2 plus dx dt plus dy dt equals 0. d2y dt2 plus dy dt minus 4 dx dt equals 0. Our initial conditions are x of 0 equals 1, x prime of 0 equals 0, y of 0 equals negative 1, and y prime of 0 equals 5. I'm going to ask you to do this work, and if you can finish it, that's great. But to make sure that we're on the same page here, what I'd like for you to do is apply the Laplace transform to the first equation, and then also to the second equation, and then we're going to use elimination. And to ensure that we're on the same page here, I'd like you to eliminate y of s, solve for x, and then maybe check back in here. Having applied the Laplace transform to both sides, substituting for the initial conditions, simplifying the equation by subtracting out what subtracts out, and then dividing through by a common factor of s, I have for the first equation the result of the quantity of s plus 1 times x of s plus y of s is equal to 1. And for the second equation, we have the quantity of s plus 1 times y of s minus 4x of s equals negative 1. In order to eliminate, I'd like the coefficients of the y of s terms to be the same. So for the first equation, I multiplied everything through by s plus 1. The second equation, I multiplied through by a negative 1. That eliminates the y of s term. And as the coefficient of x of s, we have the quantity of s plus 1 quantity squared plus 4. That times x of s is equal to s plus 2. Isolating x of s gives us s plus 2 over s plus 1, the quantity squared plus 4. I recognize this to be a cosine for the s in the numerator and a sine for the 2 in the numerator, but remember, we have this s plus 1 quantity squared in the denominator, and so there's a shift. And remember, when we're dealing with the cosine, that s plus 1 has to appear everywhere we see s. So I'm splitting up the s plus 2 into s plus 1 plus 1. Because we have s plus 1, the quantity squared, plus 4, we recognize that k is equal to 2. And to inverse transform to the sine, we need k in the numerator. So I multiply and divide by 2, eventually getting x of t is equal to e to the negative t cosine of 2t plus 1/2 e to the negative t sine of 2t. Now we need lowercase y of t. Notice that the Laplace transform for equation 1 gives us y of s, and we can easily isolate it. Y of s is equal to 1 minus the quantity of s plus 1 times x of s. But we've also got that x of s is equal to s plus 2 divided by the quantity of s plus 1 squared plus 4. Substituting in, we have y of s is equal to 1 minus s plus 1 times s plus 2 divided by the denominator s plus 1, the quantity squared, plus 4. I was going to turn you loose on this, but it gets... I mean, you can do it. We need common denominators. The way that's going to look is y of s is equal to s squared plus 2s plus 5 minus s squared minus 3s minus 2, all divided by that denominator of s plus 1, the quantity squared, plus 4. This would be problematic because we have not a proper fraction, it's an improper fraction. The degree of the numerator is the same as the degree of the denominator, and that means that the limit as s approaches infinity isn't 0, except that it is, because the s squareds subtract out. We find that y of s is equal to negative s plus 3, that negative is part of the numerator, not in front of the fraction, divided by s plus 1, the quantity squared, plus 4. Now, I'm going to split this up because we again have a cosine and a sine situation going on. For the cosine, we have this s plus 1, the quantity squared, plus 4 in the denominator. Actually, for both of them we do. Now, because of the s plus 1 quantity squared in the denominator, we have that shift, which means the numerator of the fraction that's going to become the cosine needs to have an s plus 1 in it. Let's see if we can carefully make that happen. In the numerator of the fraction directly preceding where we are, on the left, we have negative s plus 3. If I factor out a negative, then that becomes the negative of the quantity of s minus 3. I want us to have an s plus 1, so I'm going to put this negative in front of the first fraction. The easiest way to do it is inside these parentheses where I have negative in front of s minus 3 is to add 1 and subtract 1. So then the negative of s plus 1 fills the first numerator, and then distributing the negative into the minus 3 and minus 1 gives us a plus 4 for the numerator of the second fraction. That's going to inverse transform to the sine function, for which we need to note that k is equal to 2, so instead of that 4, I'm going to write it down as 2 times 2. Now I'm ready to find y of t using the inverse Laplace transform. It is equal to negative e to the negative t times the cosine of 2t plus 2e to the negative t times the sine of 2t. Now, for good form, I'm going to put the solution that we got for x of t right next to our solution for y of t, and this gives a nice presentation.